Great. So our next speaker, Maria, if you'd please share your screen.
Yeah, sure.
So the next speaker in this session is Maria Schutte from the University of Oklahoma. And she is going to tell us about modeling stellar surface activity on an M-dwarf utilizing transits from ground-based diffuser-assisted photometry.
Yes. Hi.
Great. Take it away, Maria.
Okay, great. Can everybody hear me? Yes. Okay, great. All right, so hi, yes, I'm Maria Schutte. I'm a graduate student at the University of Oklahoma, and today I'll be talking about modeling stellar surface activity on an M-dwarf with a tidally locked TRAPPIST-1 analog using data from APO. So just as a quick background on spots, so sunspots and star spots are darker sections of a star's photosphere that are linked to concentrations of magnetic activity that then inhibit the convection on the surface of the star. And we know from sunspots that they have, sunspots themselves can have umbras and penumbras, so darker spots surrounded by a sort of lighter spot. And they also tend to be circular in nature and they form in sort of groups. And we also can resolve sunspots. We can sometimes resolve them with our own eyes, at times with proper protection, and we can definitely do it with telescopes. But then the question becomes, well, how can we do this on other stars, rather other than the sun? And so the way that we do this is we do this with this program, STSP, that can model these spot positions and sizes using a transit of a secondary object. So this little video sort of shows what I'm talking about. As a companion comes, it crosses in front of the star, and we get this nice transit. And then I'll wait for it to come back around again. And as it orbits, once again, every time it orbits, if it happens to cross in front of a darker spot, it causes this bump, distinct bump that we can then see in the light curve itself. And so then we can use these bumps, we can model with our program, and that allows for a sort of robust study of individual surface activity events on a variety of types of stars that we can actually know where they are and what size they are on the surface of the star. So knowing how spotted a star is important just in general for understanding sort of the magnetic activity of a variety of types of stars. It's also important for transmission spectroscopy. So this is actually a series of light curves from space from Singh et al. 2011, and it's in a variety of wavelengths. And I'm showing this mainly to show that these transition spectroscopy events, they depend on knowing precise transit depths, but a large source of contamination for these is stellar activities. So this happened during their transits. They had this spot that occurred, and it creates a very large, like I said, bump in the transits themselves. And it also depends on wavelength. So the amount of bump that you get depends on the wavelength that you're observing in. And knowing how much of the star is covered in spots allows for a more precise determination of this contamination that you're going to get in your transmission spectroscopy for a variety of different types of stars. So we've used STSP before. In this case, we used it on a K-dwarf HAP-P11. And this was done back in 2017 by Brett Morris, who spoke earlier this week. And it was shown to have similar size spots to the sun, but with many more of them using this program. But this was using Kepler data. So this is all space-based data that we've previously been doing this with. So this is a Kepler light curve with the red STSP model, again, overplotted. And then above just shows an example of what these spots most likely look like on the surface of HAP-P11. And over the course, a 4-year period that we got from Kepler, you can then get a sort of distribution for this object. And it shows that the sizes of these spots on the K-dwarf are the same size around a solar maximum spots, but with a much longer tail out to about even 0.3. So a radius of the spot, 30% the size of the star in some cases. So we then are trying to do this on a different system. So this system was identified in the test data as actually having an M-dwarf with a possible planet. And it's an M0 type star. And we eventually found out that it's indeed not a planet, but an M8 companion, so sort of TRAPPIST-like companion. And we also found out that it's tidally locked. So the orbital period of the companion is about 1 day, and the rotation period of the star is also about 1 day. So it's rotating really quickly. And it's also an M dwarf, so we know that those are pretty active stars. And just to show you an example of another type of star, another M dwarf, a UMIC, that we also know has really large sunspots or star spots, as you can see here. But a UMIC is actually a lot younger, so it's even more active. So what we then were able to do is we were able to get a transit from APO. And like I said, originally we weren't expecting there to be a spot in this transit. So we got this transit in February, and this is in the Simrock filter, so pretty red. And we got this with the Arctic instrument plus the diffuser. This is diffuser assisted photometry in order to get the precision that we need. And we were able to actually resolve this spot in the middle of this transit, which is awesome because this is ground-based data. And so we then modeled this spot with STSP, and that's shown here again in red versus the regular transit model in cyan. And then on the right is just an example of what this spot looks like. So the blue lines depict where the M8 companion sort of crosses in front of the star. It crosses really low in the southern hemisphere. And then this is the spot itself that STSP found to be the best fit, lowest chi-squared in this case. And the radius of the spot is around 20% the size of the star, which is sort of right in between the largest size spot we found for HAT-P11, and then the largest sunspot ever is about 11%. So it's sort of right in the middle. It was found also to be like right directly in the path of the companion, where the companion crosses. And so then we saw this and we were like, oh, that's really interesting. So we decided to follow it up. So we followed up with some more data, this time in March. And we also switched filters because the eye filter, we can get a slightly better cadence. So this is on March 30th, we again observed it. And we again caught a spot. This one is not quite as prominent as the Simrock filter one, but we again fit it with STSP, and we found it's actually a similar radius, around, again, 18% the size of the star. And it's a little bit more out of the path of the planet, of the companion this time, but it's a similar longitude and a similar size. So we're seeing a month from the last time that we observed it. And so then we once again observed this object. Oh, I should also mention, we did also possibly see a dip here past what we expect, so from the regular transit model. And a dip in the light curve would indicate that there might actually be a bright spot. So it's actually brighter than the photosphere. But it's a little bit harder to model those. So we haven't quite gotten to that yet. So we then followed up again. This is actually 1 day. So we followed up the next night, again, just to try to make sure that we're seeing the same spot. And this data is a little bit, we haven't quite figured out how to perfectly detrend this yet. So that's something to note. But we did see evidence again of a spot in the same location in the light curve, which is really interesting. And so the modeling again shows a similar radius and a similar longitude. So we think that this is a persistent spot. We think this spot has really lasted for months, and it's staying there pretty much the whole time. And we again see a possible evidence of this sort of dip below what we would expect from the regular transit model, indicating there might also be a bright spot right there, because we saw it the day before as well. So with all of this, we have some future work as well. So we have some future work involving a simultaneous filter observations with the LCO Muscat3 instrument shown here on the right, which allows us to do 4 different filters all at once. And each filter has a diffuser in it. So we can get the same sort of precision that we're getting from APO's Arctic Plus diffuser that allows us to see these spots from the ground rather than from space. So this is an example of this is a G-type star, Kepler-63, that we've already done this with. And we just took this data this year. And as you can see, it's a little bit messy, but we have all 4 filters plotted here with their models, transit models below. And you can see, we see a sort of spot right here. And what we're trying to do is now pull out the contrast information so we can try to get a temperature for these spots. Previously, we had been assuming a contrast for these spots. You have to do that in order, thank you, in order to get, in order to be able to get a reliable radius for the spots, we have to assume a temperature. So we just usually start with a sunspot temperature and sort of work from there. But with this sort of work, we can actually break that degeneracy and know the temperature of the spot before we do the modeling. So that's some future work that we're hoping to do. We've done this so far with Kepler-63 and a K-dwarf, HAPI-11 that I talked about earlier. And we're hoping to also do it with this M-dwarf, so we can get a sort of full range of spectral types, almost a full range. So just in summary, STSP can model the star spot size, latitude, and longitude using the transits of these companions as a way to probe these surface features and as a way to really spatially resolve them on the surface of the stars. And so we did this for an M0 star with a tidally locked M8 companion using light curves from the ground rather than previously we were using space-based data using this diffuser-assisted Arctic photometry. And our preliminary results show that there is one persistent spot on the southern hemisphere of this star that's about 18% the size of the star, with a potential bright spot as well seen in some of the transits. And we are still investigating why this spot appears larger in the SIMROC filter data. So we're investigating if it's a contrast issue or something like that. And future work involves using this Muscat-3 instrument I just talked about. And we can also use APO with the diffuser and the sort of filter swapping technique to obtain the spot temperature, but that doesn't allow us as high of a cadence as we do with the simultaneous light curves. So that would really be transformative. And then also we would like to extend this to more systems with a variety of spectral types and rotation periods as well. And so with that, I will take any questions.
Thank you, Maria. So the first question goes to James Davenport. James?
Hi, Maria. Really cool. Really awesome to see STSP at work here. I'm curious, the multi-band imaging with Muscat-3 looks really neat, and I'm wondering if you have a sense for how faint of a star you can get down to?
Ooh, that's a good question. I'm not sure. We've only, like I said, we've only done this so far with Kepler-63 and HAPI-11, which are pretty bright. So we've only been focusing on relatively bright targets. Kepler-63 is like a 13 mag. So we haven't tried it yet with this object, which is a little bit dimmer. So it'll be interesting to see if we can actually see the spot with SCO, which is a little bit smaller of a telescope. So yeah.
Okay, second question goes to Yuta. Go ahead.
Thank you for a very interesting talk. If we look around the end of test light curve, we see a rotational modulation. And are there any implications for such rotational modulation from the information of the spot information?
You mean like the full light curve?
Yeah, any relation or implication or new, yeah.
Yes, so we do see overall spot modulation, you're right, in the full light curve. And STSP can also model that, and it's something that is also future work. So we're looking at sort of the full light curves from tests in order to sort of get the full spot modulation, and then we can sort of get an idea of what's going on, not just in the part where the planet is crossing. So yeah, we can do that with STSP.
Thank you.
Mm-hmm.
Russet, go ahead, ask your question.
Yeah, so when you said that the system, or that at least one of the systems and also your model was tidally locked, it was a little unclear if you were talking about the primary being tidally locked or the companion or both?
It's the companion in this case.
Mm-hmm.
Yeah, I'm
So-
really just talking about the rotation period is almost exactly the same as the rotation period of the host star is almost exactly the same as the orbital period. It's really all I'm trying to get at there. So there might be a better wording for that, but that's really it. Yeah.
Okay, so do we know if there's anything going on the back side of the companion star?
We don't. That would be really interesting though.
Oh, and I was very interested in the spot that you observed 2 months in a row. Is there
Mhm.
any other evidence, other observations telling us about expected lifetime of star spots?
So for this object, we tried to also observe it in April, and we got a transit, but unfortunately the data quality just wasn't good enough that night. So we just got a transit. We couldn't really get sort of good enough quality to see, but we did try to sort of, again, to try to see if it lasted even that long. But yeah, that'd be really interesting too.
Cool.
Great. Thank you, Maria.